Hello IB, this is your third day of Unit 6 and we're going to be talking about trig functions and the area between trig function and the x-axis or the trig function and another trig function. So just to start you guys off to have an idea of what we're going to be discussing, I've drawn for you just a general sine curve. So this is going to be y equals sine x in red and it's from 0 to 2 pi. And then we're looking at the area between the sine function and cosine. And we're going to be trying to discuss what this area is right here in the middle between the red sine function and the blue cosine function. So we know from our previous units that in order to figure out the area between two functions, we need to figure out when they intersect each other. So we're going to start off by setting cosine equal to sine. If we do that, anytime that you guys have a function with sine and cosine, we actually are trying to write it as tangent because then that will give us just one trig function to worry about instead of two separate ones. So I'm going to go ahead and divide by cosine because I'm trying to get tangent, which is sine divided by cosine. So if I divide by cosine on both sides, I wind up getting, well, 1 is equal to tangent. And since I'm really trying to solve for x, I'm trying to solve for the x values where these two functions intersect each other. So really I'm looking for this value and this value. Right now we don't know what they are, so I'll just call them a and b, but they're actually x values, right? And since we're drawing trig functions, our x values are our radians or our degrees, right? Depending on how you're graphing it. So in order to get x by itself, I need to look at inverse tangent of 1 to get x. Well, tangent is 1 at a 45-degree angle. Remember, we studied trig at the beginning of the year for a reason. So in the first quadrant, I'm going to get a 45-degree angle, which is positive 1 for tangent. And then the other, remember all students take calculus for your 4 quadrants. Well, all trig functions are positive in the first quadrant. Only sine is positive in the second. Tangent is positive in the third. And then cosine is positive in the fourth. So I know that tangent's positive in the first quadrant and also in the third quadrant. So that would make 45-degree reference angle in the third quadrant, which is 180 plus 45. So I'd wind up getting 225 degrees. In radians, that would be our pi over 4. And then also, so this is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, plus another reference angle of 45 degrees. So that's 5 pi over 4. So a and b values in this picture are pi over 4 and 5 pi over 4, or 45 degrees and 225 degrees. That really makes sense because by the time I get to the end of my one revolution of my sine and cosine, this is 2 pi. So it would make sense that pi over 4 is here and 5 pi over 4 is here. So we're going to go ahead and set up an integral to find the area from pi over 4, which is where they first intersect in this domain that we're given, and 5 pi over 4. The top function is the red function. Sine has higher y values than the cosine graph does. So we'll have sine, and then we are going to subtract cosine. And since this is an integral, we are taking the integral with respect to x, and we'll put our dx at the end. So since you guys spent last class talking about the antiderivative of sine and cosine, we'll go ahead and solve for what our area really is. So antiderivative of sine is negative cosine. I'm going to keep the negative sign with me. And the antiderivative of cosine is sine. And then remember, we're going to evaluate this between pi over 4 and 5 pi over 4. Okay? So we are going to go ahead and substitute in 5 pi over 4. So I've got, we'll start off with the first set, negative cosine of 5 pi over 4, and then minus sine of 5 pi over 4. Oops, close my parentheses. And then we're going to go ahead and subtract close that. Oop, parentheses and bracket. There we go. Subtract bracket. Woo, didn't like that. There we go. Negative cosine of pi over 4. Goodness. There we go. Minus sine of pi over 4. Okay. So you guys know we're talking about a 45-degree reference angle. So whether it's in the first quadrant is the pi over 4 or the third quadrant, which is the 5 pi over 4. So as we evaluate this, we're in the third quadrant with cosine. Cosine is going to be negative, right? Remember, all students take calculus. So cosine is negative in the third quadrant. 45-degree reference angle for cosine and sine is root 2 over 2. So I have negative, and then I've got cosine, so that's negative root 2 divided by 2. And then we have minus sine of 5 pi over 4, also going to be negative root 2 divided by 2. Okay? Now I'm going to subtract, and cosine of pi over 4 is just root 2 over 2, but I have this negative in front of it, so it's going to wind up being negative root 2 divided by 2. And then subtract again, bring down that negative. Sine of pi over 4, again, is root 2 divided by 2. I keep all these parentheses here, though, because this negative has to distribute. So we wind up getting positive root 2 divided by 2, another positive root 2 divided by 2, and then distribute the negative, another positive. We'll get root 2 divided by 2, and then another positive root 2 divided by 2. All right, so that gives us 4 root 2 divided by 2's. If I divide 4 by 2, simplify this, we get 2 root 2. And we're talking about units. There we go. Units squared, because we're talking about area, but we were not given specific units, like whether this was centimeters or meters or what our graph was actually measuring. So 2 root 2 units squared, and again, that was this area between the red and the blue, which was between cosine and sine, between the first and third quadrants. All right, where that enclosed area was. So this is just one example of how we can find enclosed area using trig functions. Let's go to one that's actually a little bit simpler. It's just the trig function and the x-axis, but we're looking at it slightly differently because it's split into two pieces. We want to find the area between 4 pi over 3 and 2 pi, but the way that this IB question lays it out for you, you want to find them separately. So this IB question tells you the following diagram shows a part of the graph of cosine. So this is actually cosine x. And it's between 0 and 2 pi as labeled, right? And regions A and B are shown. So the very first question is asking us to write an expression for the area of A. Well, just an expression would mean to find the area between the curve and the x-axis, that by definition is the integral, from 3 pi over 2, which is where it crosses the x-axis, to 2 pi, which is the end of this enclosed area. And the function we're dealing with, or the function that we want to find the area, underneath is the cosine graph with respect to x. That is an expression, doesn't say to solve, so part A is complete. Part B asks you guys to solve it. So I am actually going to take the antiderivative. So the antiderivative of cosine is negative sine, or excuse me, positive sine. There we go. Because the derivative of sine is cosine. So the antiderivative of cosine is sine. And I'm going to evaluate between, again, 3 pi divided by 2 and 2 pi. So that means I'm trying to find sine of 2 pi and then subtract that with sine of 3 pi over 2. All right? Again, we'll simplify this because it is asking us to calculate. So let's go ahead and calculate. Sine of 2 pi is 0. Remember, sine is your y value. So at 2 pi, which is on the x-axis, it's 0. Your y value is 0. 3 pi over 2 is 270 degrees. So that our y value is negative 1 there. So now I have minus, and then sine of 3 pi over 2 is negative 1. So I wind up with 1. And it says area of A, so we are actually finding this is 1 unit squared. I do not believe this problem gave us units. Nope, so then we just use the general unit squared. Then it says find the total area of the shaded region. So right now, this 1 unit squared that I just found in part B, that is this space right here. So I just found that this whole area here is 1 unit squared. What I really would like to find is this area here. I don't have that. So from 4 pi over 3, I need to find from 4 pi over 3 to 3 pi over 2, I need to find this area. The way that this is set up, though, is that the x-axis is on top. If I just put cosine here, I'm going to get a negative answer, and then I would have to take the absolute value of it. Or I could set it up as an area between two functions, where the first function is y equals 0, minus the bottom function, or the lower function, which is the cosine of x. And I'll still take the antiderivative with respect to x. Since it says to find the total area of the shaded regions, I'm going to have to add on whatever I get from this integral with the 1 unit squared that I got from part B, because that's the area of A, part A in the picture. So let's go ahead and find out what the area is. The antiderivative of cosine, again, is sine, but since I have this negative sign in front of it, I'm going to get negative sine for this one. And I will evaluate between 4 pi over 3 and 3 pi over 2. So if I substitute 3 pi over 2, again, that is negative. Sine of 3 pi over 2 is going to be negative 1 minus, and now I have negative sine of 4 pi over 3. So 4 pi over 3, remember, are special angles. 4 pi over 3. Pi over 3 is 60 degrees, and so 4 pi over 3 would wind up being a 60-degree angle in the third quadrant. Well, sine of 60 degrees is going to be opposite over hypotenuse, so that's going to be your square root of 3 over 2. If it's in the third quadrant, it's negative, so that means we are talking about a negative square root of 3 divided by 2. All right, that's a lot of negatives to keep track of. We have the negative from the original. Sine x, or sine of 3 pi over 2 is negative 1. And then we had minus negative, again from the sine, and then sine of 4 pi over 3 is negative square root of 3 over 2. So I'm going to go ahead and extend the page. And this comes out to be a positive 1. This is positive, but then you have another negative, so minus root 3 over 2. Okay? So I have a common denominator. I'm going to change this 1 to 2 over 2. So now I have 2 minus root 3. Oh, let's try that again. Okay, minus root 3 divided by 2. And then I'm going to add the 1 from the other area, because this is region B. Region A is 1. Equals, I'm going to change this 1 to a 2 divided by 2. So now I have 2 plus 2, so I'm going to get 4 minus root 3 divided by 2. And that is my unit squared. All right, so this is a pretty straightforward problem. They gave us 1 point each for setting up the integral, finding the integral, and then 4 points for putting the two together. We're going to look at one last example. I've already started this one for you. You guys are asked to find, right off the bat, the antiderivative of 1 plus 3 sine x plus 2. When this plus sign, you guys can separate this as two separate terms. So the antiderivative of 1 becomes x. 3 is your coefficient. Antiderivative of sine is negative cosine, and then the inside remains the same. The derivative of the inside is 1, because derivative of x plus 2 is just 1, so you don't have to worry about dividing by the derivative of the inside. If I simplify this, the 3 will distribute, or just multiply, so I'll get x and then minus 3 cosine of x plus 2. It's indefinite, so I put the plus c on it. The second part shows that below is the region from 0 to a of the function you just took the antiderivative of. Since the shaded region goes from 0 to a and a is not quite at 2, we're supposed to find this point A. Well, really, the point A is just an x-intercept, so we can use our calculator to graph and find the x-intercept.